Hello, my dear GATE aspirants, my dear beloved students. Right, welcome to the ESE online platform. I am Malakondaya Gandham, faculty, thermal faculty at ESE Engineering Academy. Dear friends, I have more than 25 years experience in the teaching field. I am very comfortable with almost all thermal oriented subjects. Today we are going to discuss the most important concepts for the subject thermodynamics. This lecture is very useful for those students who are going to write the GATE and ESE in the year 2024. I have taken some concepts where generally the students are feeling difficult. Those concepts are the preparation strategy we have discussed in the last video. In this video, we are going to discuss only the important concepts on the subject of thermodynamics. Okay? I have taken the important concepts like point function and path function quantities, relation between non-flow work and steady flow work, Clausius inequality equation, entropy change between the two systems, triple point state, sublimation, desublimation, Clausius-Clapeyron equation, chemical dehumidification process, nozzles and diffusers. These are the areas generally students are confusing or students are feeling difficult. That's why I have taken these important concepts to explain the each and every one very clearly or crystal clear manner. Okay? So without wasting the time, let us take the very first concept, that is point function quantities and path function quantities. What is meant by point function quantity? Very simple, the quantity which is depending on only state of the system. The quantity which is depending on only state of the system is called point function quantity. Example for point function quantity: all thermodynamic system properties. All properties are coming under point function quantities only. Let us take the point function quantities in one side and path function quantities in other side. Point function quantity means the quantity which is depending on state of the system is called point function quantity. Example, all thermodynamic system properties like pressure, volume, temperature, enthalpy, entropy, etc. These are all coming under point function quantities. Now come to the path function quantities. Path function quantity means the quantity which is not only depending on initial and final states, but also depending on the route followed by the process or path followed by the process, is called path dependent quantity or simply path function quantity. Once again, the quantity which is not only depending on the initial state and final state of the system, but also the history of the process or path followed by the process, is called path function quantity. Okay? Example for path function quantity: thermodynamic heat, thermodynamic work and entropy generation. Entropy generation also coming under path function quantity, whereas the entropy transfer, the entropy I wrote here, that is the entropy transfer. Entropy transfer is coming under point function quantity, whereas entropy generation is coming under path function quantity. Okay. The other important difference between these two is all point function quantities are operating with the exact differential d. Therefore, all point function quantities are also called the exact differentials. You know, mathematically, d is used for exact differentiation, d bar or del is used for inexact differentiation. All point function quantities are operating with the exact differential d. Therefore, all point function quantities are coming under exact differentials like dp, dt, ds, dh, etc. Whereas path function quantity is not only depending on the initial and final states, but also the route followed by the process. That kind of quantity is coming under path function quantity. Path function quantity is coming under inexact differential denoted with del, like del q, del w and del S generation, etc. Entropy, generation, etc. Del S generation. Similarly, the other important difference is the point function quantities can be written by their difference like this. Integral 1 to 2 dp can be written as p2 minus p1 because the point function quantities are depending on initial and final states. Similarly, integral 1 to 2 dh can be written as h2 minus h1. Okay. Similarly, integral 1 to 2 dv can be written as v2 minus v1. But path function quantities cannot be written by their difference. Path function quantities cannot be written by their difference because these are depending on the route followed by the process. Therefore, integral 1 to 2 del q should not be written as q2 minus q1. You should not write like this, but it can be written as either q122 or q122 like this or simply q. Similarly, integral 1 to 2 del w cannot be written as w2 minus w1, but it can be written as w122 or w122 or simply w. Okay na? Similarly, the other important difference is for any thermodynamic cycle, cyclic integral, the circle with integration is called cyclic integral. Dear friends, remember the symbol cyclic integral is used for only thermodynamic cycle. Okay? For any thermodynamic cycle, cyclic integral, any point function quantity is equal to 0. Cyclic integral, any point function quantity equal to 0, but cyclic integral path function quantity never be equal to 0. Never be equal to 0. The symbol cyclic integral represents sum for a complete cycle. Sum for a complete cycle. Complete cycle. Now let us see how the cyclic integral point function quantity equal to 0 and how the cyclic integral path function quantity is not equal to 0. For that, let us take any thermodynamic cycle like the simplest cycle, Otto cycle. As we all know, the Otto cycle consists of 4 processes. 2 are reversible adiabatic type isentropic process and 2 are isochoric process also called as constant volume process. So Otto cycle consists of an isentropic compression followed by constant volume heat addition followed by an isentropic expansion process followed by constant volume heat rejection process. Okay? For that particular cycle, the cyclic integral point function quantity, any point function quantity, let us take cyclic integral pressure. Cyclic integral pressure. Cyclic integral pressure is written like this. Assume the pressure of the material at state 1 is P1, at state 2 is P2, pressure at state 3 is P3 and pressure at state 4 is P4. Then cyclic integral pressure, right, for that thermodynamic cycle is P2 minus P1, that is for the very first process. Pressure is coming under point function quantity or point dependent quantity. Straight away you can write pressure at state 2 minus pressure at state 1 plus for the 2 to 3 process P3 minus P2, P3 minus P2, for the 3 to 4 process plus P4 minus P3, the final pressure minus initial pressure for that particular process plus for the last process final state is 1. Therefore, the P1 minus P4 is the pressure difference for the last process. That is the meaning of cyclic integral any point function quantity like pressure. Now look at the right relation, plus P2 minus P2 cancel, minus P1 plus P1 cancel, plus P3 minus P3 plus P4 minus P4 is equal to 0. Cyclic integral any point function quantity, of course point function quantity can also be called as state function quantity equal to 0, whereas cyclic integral path function quantity, let us say cyclic integral path function quantity like thermodynamic work, cyclic integral thermodynamic work del W is equal to, assume the work interaction for the 1 to 2 process W1 to 2, for the 2 to 3 process W2 to 3, for the 3 to 4 process W3 to 4, for the 4 to 1 process W4 to 1. Here you should not write W2 minus W1 because work is depending on path followed by the process. So cyclic integral thermodynamic work means work for 1 to 2 plus work for 2 to 3 plus work for 3 to 4 plus work for 4 to 1. That is the meaning of cyclic integral path function quantity like thermodynamic work, right? And one more important information is the thermodynamic cyclic process can be possible with only closed system. Then what is the closed system work interaction formula? Non-flow work equal to PdV. Of course integral 1 to 2 PdV, that is the non-flow work. Now look at the 2 to 3 process. For the 2 to 3 process change in volume 0, therefore if this dV is 0, the non-flow work is 0. It means the non-flow work at constant volume equal to 0. Therefore I can write that the work for 2 to 3 equal to 0 and work for 4 to 1 also equal to 0 because 4 to 1 also coming under the constant volume process. Then the work for 2 to 3 0, work for 4 to 1 also 0. Then what is the cyclic integral? What is the cyclic integral? Thermodynamic work is equal to work for 1 to 2 plus work for 3 to 4. Work for 1 to 2 plus work for 3 to 4. Okay. Now, as you know, the cyclic process can be possible only with closed system. Closed system work is non-flow work is equal to PdV. Since PdV is the non-flow work, area towards the volume coordinate with PV diagram is the non-flow work. It means area below the PV diagram for a particular process is equal to non-flow work. Okay. Now look at the remaining process. Anyhow, work for 2230, work for 4210. Then cyclic integral thermodynamic work equal to work for 122 plus work for 324. Okay. Now look at the 122. 122 is the compression process. Therefore I can write that work for 122 definitely negative, because for compressing the gas I need to spend the work energy. Okay. That is the practical reason why we are assuming the compressors are, why we are treating compressors are power consuming devices or demanding devices. Whereas 3 to 4 process is expansion process. All expanders are coming under power developing systems. Thermodynamically, if work is available from the system, that work is taken as positive work. It means work for 122 is negative, work for 3 to 4 is positive, because 3 to 4 is coming under expansion process. Work for 3 to 4 is positive. Okay. Now come to the cyclic integral path function quantity. This is negative work, this is positive work. Then cyclic integral thermodynamic work will become 0 only when W122 equal to W324. But what is the work for 122? Work for 122 equal to area below 122. What is the work for 324? Area below 34. From the diagram it can be concluded that area below 34 is more than area below 122. Okay, let me write that point. Work for 122 is equal to area below 122, whereas work for 324 is area below 34, area below 34. From that you can conclude that area below 34 is more than area below 122. It means this area below 34 is more than area below 122. From this I can conclude that work for 324 is more than work for 122. It means positive work. Work for 324 is positive, right? Work for 122 is negative. Positive work is more than negative work. Let us say this positive work is 5 kilojoules per kilogram and a negative work is 2 kilojoules per kilogram. Then this is equal to what? Minus 2 plus 5 is equal to 3, which is greater than 0 or other than 0. Of course, for all, right, power producing systems, the network is positive, right? The thermodynamic cycle should be constructed in the clockwise direction for power producing devices, whereas for power consuming device like refrigeration system or air compressor mechanism, the cycle must be constructed in the anti-clockwise direction. Once again, wherever you find the thermodynamic cycle in the clockwise direction means that cycle is for power producing device. Wherever you find the thermodynamic cycle in the anti-clockwise direction, that cycle is for power consuming system. Since it is constructed in the clockwise direction, this is for power producing device. That is the reason why we got the network is positive. If it is in the anti-clockwise direction, network may be negative. Anyhow, cyclic integral, conclusion is cyclic integral thermodynamic work is not equal to 0. That means indirectly network for any thermodynamic cycle is not equal to 0. And one more important information is that network is positive for power producing device, for power producing device, for power producing cycle like Otto cycle, diesel cycle, Rankine cycle, Brayton cycle, etc. Similarly, that network is negative for power consuming cycle, power consuming cycle like refrigeration cycle, air conditioning systems, etc. I hope all of you clearly understood the differences between the point function quantities and path function quantities. Is it clearly understood? Yes. Then look at the another important concept, that is relation between non-flow work and steady flow work. Whatever the work interaction formula we are deciding for a closed system is called non-flow work. That non-flow work mathematical formula is equal to PDV. Whatever the work interaction formula we are deciding for open system, particularly for a steady flow system, is called steady flow work. Dear friends, remember the steady flow work equal to minus VdP. Non-flow work is PDV, whereas the steady flow work is minus VdP. Okay? Since the non-flow work is PDV, area towards the volume coordinate in the PV diagram is the non-flow work. That means area below the PV diagram is representing the non-flow work. That too, that is non-flow reversible work. Since steady flow work is minus VdP, area towards the pressure coordinate in the PV diagram is the steady flow work. It means simply area below the PV diagram non-flow work, area behind the PV diagram is steady flow work. It is like this. If I take the pressure versus volume coordinate system, let me mark a curve for expansion process. As you know, in the expansion process, the pressure of the material decreases by the time the volume increases. This may be the representation of a kind of expansion. 1 to 2 is a kind of expansion. Okay? If I assume that expansion curve is drawn for a closed system work is non-flow work. Therefore, the non-flow work formula is what? PDV. Therefore, the area below the PV diagram is the non-flow work. Let us say 1 to KL1. Area 1 to KL1 is non-flow work. So, non-flow work is equal to area 1 to KL1. That is the non-flow work. Okay? But if I assume that the same expansion curve is drawn for open system, particularly for steady flow system, area towards the pressure coordinate or area behind the PV diagram is the steady flow work. This area is representing steady flow work. From that you can write that area behind the PV diagram is steady flow work. Area below the PV diagram non-flow work. Let us assume this is the M, N. Then what is the steady flow work? Steady flow work equal to area. Tell me area 1, 2, m, n, 1. Area 1, 2, m, n, 1. That is the steady flow work. But what is our concept? Relation between the non-flow work and steady flow work. Let us see what is the relation between the non-flow work and steady flow work. Okay. So since the area 1, 2, m, n, 1 is the steady flow work, that steady flow work I am going to write like this. This steady flow work equal to, first I am taking this rectangular strip, right? That means area 1L 0 N1 plus area below 122. For getting this hatched area, first I am taking this rectangular strip area. I am adding this rectangular strip area with area below 122 is covering the total area. But for getting this hatched area, from the total area, you subtract this downside rectangular area. Okay? So that can be written like this. Area 1L 0 N1, 1L 0 N1, that is covering this rectangular strip area plus area below 122, area below 122, that is covering the total area, but I want only this area. For that I need to subtract this bottom side rectangle area, that is minus area 2K 0 M2, area 2K 0 M2. Okay? Are you following? Yes. Then let us mark the pressure and volume limits. Corresponding to state 1, pressure is P1, volume is V1. Corresponding to state 2, pressure is P2 and volume is V2. Then what is the rectangular strip area like 1L 0 N1 in terms of pressure and volume? Depth multiplied by breadth. This area is equal to P1 V1 plus area below 122. What is the area below 122? Non-flow work only. Area below 122, right? Area below 122 means area 1 to KL1 is the non-flow work. Non-flow work minus this area. This area is what? This rectangular strip area, that is right, breadth multiplied by, that is depth multiplied by breadth. P2 into V2. P2 V2. From this I can write that the steady flow work equal to, right, P1 V1 minus P2 V2 plus non-flow work. Non-flow work. That is the relation between steady flow work and non-flow work. I hope all of you clearly understood. Understood or not? Yes. Similarly, let us take the another important concept, Clausius inequality equation. Clausius inequality equation. You know, remember, this Clausius inequality equation is deciding whether your practically constructing engine is existing or not. Okay? Now let us see Clausius inequality equation. You know, Carnot cycle efficiency or reversible cycle efficiency which is operating between two temperature limits. You know, Carnot cycle is having only two temperature limits, maximum temperature and minimum temperature. Since Carnot cycle is having only two temperature limits, Carnot cycle can also be called as 2T cycle or constant temperature cycle. Whereas for the Otto cycle, right, Otto cycle is having two volume limits. That is the reason the Otto cycle is also called 2V cycle or constant volume cycle. Similarly, look at the Brayton cycle. is also called Joule cycle. The Brayton cycle is having two pressure limits. Right. Since the Brayton cycle is having two pressure limits, Brayton cycle is also called as 2p cycle or constant pressure cycle. Anyhow, Carnot cycle is also called as constant temperature cycle. Otto cycle can also be called as constant volume cycle. The Brayton cycle is also called as constant pressure cycle. Since Carnot cycle is having two temperature limits, the efficiency of the Carnot cycle is generally deciding in terms of two temperature limits. Whereas Otto cycle is having two volume limits. Therefore, the efficiency of the Otto cycle we are deciding in terms of volume ratio, that is called compression ratio. Similarly, the Brayton cycle efficiency is generally deciding, right, in terms of pressure ratio, because the pressures are the limiting values for the Brayton cycle. Okay. Anyhow, for the Carnot cycle, efficiency equal to 1 minus heat rejection dividing by heat supplied. That is the Carnot cycle efficiency. Of course, right, dear friends, remember, efficiency of any heat engine is equal to 1 minus heat rejection by heat supplied. This formula can be applicable for all heat engines, whether that heat engine is working with air as working material or vapor as working material, whether that heat engine is working, right, with two temperature limits or two volume limits or two pressure limits. It is applicable for irreversible heat engine also. So this is the general formula for deciding the efficiency of any kind of heat engine. That heat engine may be either reversible type heat engine or irreversible type heat engine. Okay? But remember, the heat engine which is working with all reversible process, the heat engine which is working with all reversible process with only two temperature limits, the heat transfer is proportional to temperature. Therefore, 1 minus Q2 by Q1 can be written as 1 minus T2 by T1. This relation you might have studied with the Carnot cycle. Once again, for any reversible heat engine, right, if it is operating, for any reversible heat engine which is operating with the two temperature limits, the heat transfer or heat ratio is proportional to temperature ratio, or heat transfer is proportional to temperature. Okay. From this, I can write that Q2 by Q1, let us compare these two relations, Q2 by Q1 equal to T2 by T1. Heat ratio equal to temperature ratio, where Q1 equal to heat supplied, Q1 equal to heat supplied, Q1 equal to heat supplied, Q2 equal to heat rejection, Q2 equal to heat rejection, Q2 equal to heat rejection. Okay. Thermodynamically, heat supplied is taken as positive. Thermodynamically, heat supplied is taken as positive. Heat rejection is taken as negative. Heat rejection is taken as negative. Okay. Now, that can be also written as, we have written Q2 by Q1 is equal to T2 by T1. This can be also written as, right, Q1 by T1 is equal to Q2 by T2. Okay. Remember, the Carnot cycle is coming under reversible cycle. For a reversible cycle, assume the heat supplied Q1 is equal to, 2000 kilowatts. At a temperature T1, that is source temperature, equal, let it be 1000 Kelvin. And the heat rejection Q2, I can say Q1 dot, Q2 dot, Q2 equal to, let it be some 800 kilowatts. The T2, temperature where the heat is rejecting, let it be 400 Kelvin. 400 Kelvin. Then what is the Q1 by T1? Q1 by T1. From this I can write that Q1 by T1 is equal to 2000 by 1000 equal to 2 kilowatts per Kelvin. Then what is the Q2 by T2? Q2 by T2 equal to Q2 by T2 equal to, it is equal to 800 by 400 also equal to 2 kilowatts per Kelvin. The reason why I have taken these values is Q1 by T1 must be equal to Q2 by T2 for any reversible cycle operating between the two temperature limits. Okay? But as you know, the Q2 is the heat rejection. Thermodynamically heat rejection is taken as negative. Therefore, I can say that this quantity is negative quantity. This quantity is negative quantity. Q1 is the heat supplied. Right? Heat supplied is positive. This quantity is positive quantity. Positive quantity. Okay? Then, if I add these two quantities, Q1 by T1 plus Q2 by T2, Q1 by T1 equal to Q2 by T2 equal to how much? Q1 by T1 2 kilowatts per Kelvin plus Q2 by T2. Q2 by T2 is minus 2 kilowatts per Kelvin plus 2 minus 2 equal to 0. 0. From this I can write that cyclic integral del Q by T is equal to 0 for what kind of cycle? For a reversible cycle. So cyclic integral del Q by T equal to 0 for a reversible cycle. A reversible cycle. Okay? Let us take the another slide. We got cyclic integral del Q by T equal to 0 for a reversible cycle. A reversible cycle. Right? Now, let us take the irreversible cycle. Let us take the irreversible cycle. For irreversible cycle. Irreversible cycle. For irreversible cycle, I am supplying the same amount of heat. Q1 for reversible cycle is equal to Q1 for irreversible cycle. For reversible cycle, I have taken the heat transfer is 2000 kilowatts at a temperature of T1. T1 right equal to 1000 Kelvin. 1000 Kelvin. Next, dear friends, remember, though you are supplying the same amount of heat energy for both reversible cycle and irreversible cycle, the network output of the irreversible cycle always less compared to work output of the reversible cycle. It means you take the practical petrol engine. Though you are burning the same amount of petrol in the reversible heat engine and irreversible heat engine, since the petrol firing in both reversible heat engine and irreversible heat engine both are same, the heat liberation or the heat liberated due to burning of the same quantity of petrol is remaining same for both reversible heat engine and irreversible heat engine. But though the same amount of heat is liberated by burning the same quantity of petrol in both reversible heat engine and irreversible heat engine, the work output of the irreversible heat engine always less than the net work output reversible engine because of the irreversibilities, because of the internal irreversibilities. Okay? For that, let us decide the reversible work. That means work output of the reversible heat engine. Work output of the reversible heat engine equal to heat supplied minus heat rejection. Dear friends, remember, heat supplied minus heat rejection is giving the net work output for any kind of heat engine, whether that heat engine may be reversible heat engine or irreversible heat engine or reversible cycle or irreversible cycle. Anyhow, the work output of the reversible cycle is Q1 minus Q2. Q1 is 2000, Q2 is 800, right? 2000 minus 800 is equal to 1200 kilowatts. That is the expected net work output from the reversible heat engine. Okay? But what I am trying to tell is, though you are supplying the same amount of heat for both reversible cycle and irreversible cycle, the net work output of the irreversible cycle always less than that of reversible cycle. This net work output of the reversible cycle, we have decided, how much we have decided, right? 1200 kilowatts, 1200 kilowatts. From this we can decide the net work output of the irreversible heat engine. The net work output of the irreversible heat engine is less than that of reversible heat engine. You take any value of net work output for irreversible engine which is less than this one. Let us say 1000 kilowatts. 1000 kilowatts. Then what is the work output of the irreversible engine? Work output of irreversible engine equal to the heat supplied for irreversible engine minus heat rejection for irreversible heat engine. Okay. What is the net work output of the irreversible heat engine? Based on this value, you can take any value which is less than this 1200 kilowatts. Any value which is less than that reversible work. I have taken 1000 kilowatts. 1000 equal to heat supplied for irreversible heat engine 2000 minus heat rejection for irreversible heat engine. From this, the heat rejection for irreversible heat engine equal to 2000 minus 1000 is equal to 1000 kilowatts. 1000 kilowatts. That means for the same amount of petrol burning in both reversible heat engine and irreversible heat engine, the heat rejected by irreversible heat engine is more compared to the heat rejection from reversible heat engine. Okay. Anyhow, heat rejection for irreversible heat engine is, right, 1000 kilowatts at a temperature T2 equal to same as the reversible heat engine cold source temperature, that is 400 Kelvin. 400 Kelvin. Then what is the, listen carefully, what is the Q1 for irreversible engine dividing by T1 for irreversible engine plus Q2 for irreversible engine dividing by T2 for irreversible engine equal to Q1 by T1. Q1 is 2000. Let me write it clearly. 2000 dividing by 1000. Dividing by 1000. Q2 for irreversible heat engine. Q2 for irreversible, Q2, right? Q2 is the heat rejection. Q2 is the heat rejection. This quantity is negative. Negative. Minus, right, 1000 dividing by, right, dividing by T2, 400. 400. Let me take another slide. Q1 for irreversible engine dividing by T1 for irreversible engine plus Q2 for irreversible engine divided by T2 for irreversible engine equal to 2000 by 1000 equal to 2 minus 1000 by 400, 2.5. 2.5. It is equal to minus 0.5, which is less than 0. Less than 0 is for what kind of cycle? Yes, irreversible cycle. For irreversible cycle, cyclic integral del Q by T less than 0. For irreversible cycle. Irreversible cycle. Anyhow, from this I can conclude that cyclic integral del Q by T less than 0 for irreversible cycle. For irreversible cycle. Then, right, for a reversible cycle, cyclic integral del Q by T equal to 0. For irreversible cycle, cyclic integral del Q by T less than 0. Let us combine these two. Cyclic integral del Q by T less than or equal to 0. Right? This particular equation was given by Clausius. Therefore, this equation we are calling as Clausius inequality equation. Clausius inequality equation. Okay. So let me take another slide. Cyclic integral del Q by T always less than or equal to 0. This particular equation is called Clausius inequality equation. Okay. Dear friends, remember cyclic integral del q by t equal to 0 for any reversible cycle. Any reversible cycle. Next, cyclic integral del q by t less than 0 for any irreversible cycle. You take the irreversible cycle like vapor compression refrigeration system. Generally, vapor compression refrigeration system is constructing with a capillary tube. Capillary tube is working on throttling process. Throttling process is highly irreversible process. Irreversible cycle means if any cycle is constructed with all irreversible process or at least one irreversible process is called irreversible cycle. Once again, if any cycle is constructed either with all irreversible process or at least one irreversible process, that kind of cycle is called irreversible cycle. The best example for irreversible cycle is vapor compression refrigeration cycle. Whereas Otto cycle is constructing to work with all reversible process. Similarly, diesel cycle, dual cycle, Stirling cycle, Ericsson cycle, Rankine cycle, Lenoir cycle, Brayton cycle, these are all cycles constructing with all reversible process. That kind of cycles are coming under reversible cycles, right? So, reversible cycle like Otto cycle or diesel cycle, etc. Okay, dear friends, remember cyclic integral del q by t greater than 0 is impossible. Cyclic integral del q by t greater than 0 is impossible. I hope all of you clearly understood about the Clausius inequality equation. Understood or not? Yes. Then look at the another important concept, entropy change between the two systems. Entropy change between the two systems. First, let us take the entropy change between the two sources. You know, thermodynamically source means, sources are two types, hot source and cold source. Thermodynamic source means which is maintaining constant temperature irrespective of the amount of heat receiving or irrespective of the amount of heat losing. Thermodynamically, there are two sources, namely high temperature reservoir is also called hot source, low temperature reservoir is also called cold source. The hot source is one which can give any amount of heat for you without dropping the temperature. The hot source is one, it can give any amount of heat for you without dropping the temperature. Whereas the hot body can give only a finite amount of heat energy by the time the temperature of the hot body decreases. Similarly, the cold source is one which can receive infinite amount of heat energy without gaining the temperature. Once again, the cold source is one which can receive infinite amount of heat energy without raising the temperature. Example for cold source, river water, atmospheric air, the sea water, lake water, pond water. Even if you dump the bucket of hot water with the lake water temperature cannot be changed. Therefore, lake water can be treated as the cold source. Similarly, all our automobile vehicle engines are dumping the heat to atmospheric air. Atmospheric air temperature cannot be changed. Therefore, atmospheric air itself is treated as cold source, is generally called as sink. Anyhow, right, the cold body is one which can receive only a finite amount of heat energy, right, by increasing the temperature. That means by the time the cold body is receiving heat energy, its temperature increases. By the time the hot body is losing energy, its temperature is dropping. But hot source can maintain constant temperature, though it is continuously giving any amount of heat for you. Similarly, the cold source is one, it can receive infinite amount of heat energy from you without gaining the temperature. Yes. Then let us take the hot source. Assume that hot source is maintaining the temperature T1 and cold source let us take the cold source. Cold source is maintaining the temperature T2. When you keep the hot source and cold source side by side, naturally the heat is transferring from hot source to cold source. Let us say del Q amount of heat is transferring from hot source to cold source. Okay? Dear friends, remember this del Q is coming under negative with respect to hot source. The same fellow comes under positive with respect to cold source, because the cold source is receiving this much amount of heat energy, whereas the hot source is losing that much amount of heat energy. Thermodynamic sense is that heat supplied is taken as positive, heat receiving is taken as positive, heat losing is taken as, or heat rejection is taken as negative. Okay? Then what is the change in entropy? Change in entropy, net change in entropy, I can write like this. Net change in entropy equal to change in entropy, change in entropy of the hot source, change in entropy of the hot source plus change in entropy of the cold source, change in entropy of the cold source. It is equal to, generally heat transfer by dividing by del Q dividing by temperature is giving the change in entropy ds. That is the general formula. Then the ds for hot source equal to del Q by T, but that is negative because the hot source is losing that much amount of heat energy, plus ds for cold source del Q by T, del Q by T. That is how you can decide the net entropy change between the hot source. Dear friends, remember, while we are deciding the entropy change, right, with heat transfer at constant temperature. You know, not only hot source and cold source can maintain constant temperature, but also during the condensation process temperature remains constant. During the freezing process temperature remains constant. During the sublimation, desublimation, vaporization, right, these are all the processes which are maintaining constant temperature. While we are finding the change in entropy at constant temperature, you need to decide the direction of heat transfer for that particular process where the heat is happening or heat transfer is happening at constant temperature. See, that means let us take the condensation process. In the condensation process, what is happening? The heat is rejecting. Therefore, the heat rejection during the condensation is taken as negative, minus del Q divided by condensation temperature. Whereas during the vaporization process, for the vaporization process we are supplying the heat, but temperature is remaining constant. Since the material is receiving the heat energy for vaporization purpose, right, that material receiving energy, heat energy is taken as positive, del Q by T plus del Q by T is the change in entropy for vaporization, whereas minus del Q by T is the change in entropy for condensation process. That means I am trying to tell, right, what I am trying to tell is, while we are finding the change in entropy at a constant temperature, you should be very careful that the del Q should be decided. The del Q, that means heat transfer, should be decided whether that is positive or negative. But while the heat transfer is happening with the bodies where the temperature is changing, you need not to decide the direction of heat transfer. Your calculator itself is giving the change in entropy whether it is positive or negative, like this. For that, let us take the hot body, and cold body. First I have taken hot source and cold source, but I am taking here hot body and cold body. Assume the hot body initial temperature is T1H. Hot body initial temperature is T1H, right? एक minute. Hot body initial temperature is T1H. Next, by the time the hot body is giving the heat energy to cold body, that means once you keep the hot body, cold body side by side, naturally heat is transferring from hot body to cold body. By the time the hot body is giving the heat energy, its temperature is dropping from T1H2 to T2H. Okay? Now assume initial temperature of the cold body T1C. By the time the cold body is receiving heat energy, its temperature is increasing from T1C to T2C. Since the cold body is receiving heat energy, I can say that T2C is more than T1C, whereas this fellow is losing the energy, I can say that T2H is less than T1H. T1H. Okay? Next. Dear friends, remember, if hot body and cold body are maintaining either solid or liquid, you need not think about the specific heat, or you need not think about where that hot body is working, whether it is at constant pressure or constant volume, because solids and liquids are maintaining only one specific heat. But if the hot body is maintaining some gas and cold body also maintaining some gas, since gases are maintaining two specific heats, namely specific heat at constant pressure and specific heat at constant volume, you need to decide where the hot gas is dumping the heat and cold gas is receiving the heat, means at what process. For that, assume the gas present in the hot body is maintaining constant pressure and the cold gas is receiving the heat at constant volume. Different process I have taken. You can also take the same process. Okay? Then the change in entropy of the hot body is equal to del Q by T. But del Q equal to what? Mass, right? Mass of the hot body into the specific heat at constant pressure of the hot body, because we are assuming that hot body is losing as a gas at constant pressure, into dt. dt means change in temperature dividing by temperature. Okay? It can be also written as change in entropy of the hot body is equal to mass of the hot body, specific heat at constant pressure of the hot body into dt by T. So this is the small change in entropy of the hot body with small change in temperature dt. For getting the overall change in entropy, upon integration and apply the limits from 1 to 2, then the S2 minus S1 for the hot body is equal to mass of the hot body into Cp of the hot body into, right, you know this part is directly I am writing ln T2 of the hot body dividing by T1 of the hot body. Now look at the T2 of the hot body. T2 of the hot body is less than T1 of the hot body. That means T2 is less than T1. This is a fractional value. ln fractional value always negative. That means change in entropy of the hot body is negative. That will be decided by your calculator. You should not take here minus del Q. Got that point? But in the hot source condition, we have taken minus del Q by T because it is maintaining constant temperature. It means wherever the entropy change is to be decided at constant temperature, in addition to magnitude of heat, you need to decide the direction of heat. But wherever the heat is transferring with a change in temperature, you need not to decide the direction of heat transfer. Your calculator itself is showing the change in entropy, whether it is positive or negative. Anyhow, this is the negative change in entropy. Your calculator will give. You need not to write it. Similarly, the change in entropy of the cold body. Change in entropy of the cold body equal to del Q of the cold body dividing by temperature equal to mass of the cold body. Where the cold body is working at constant pressure, the CV of the cold body into dt of the cold body dividing by temperature. So that is a small change in entropy ds with small change in temperature dt. For getting the overall change in entropy, upon integration and apply the limits from 1 to 2, you can write S2 minus S1 for the cold body is equal to mass of the cold body, CV of the cold body into ln T2 of the cold body divided by T1 of the cold body. T1 of the cold body. But look at the T2 of the cold body. T2 of the cold body is more than T1 of the cold body. This T2 is more than T1. Therefore, this T2C by T1C greater than 1. Ln greater than 1, always positive value. Positive value multiplied with positive quantities, always positive. The change in entropy is greater than 0 or positive. Change in entropy is greater than 0, or I can also write positive. Calculator will show it. Then what is the net change in entropy? Net change in entropy is also called universe change in entropy, equal to, right, change in entropy S2 minus S1 with respect minus S1 with respect to cold body. That is how you can decide entropy change between the two bodies and entropy change between the two sources. Okay, I hope all of you clearly understood. Similarly, look at the another important concept: triple point state, sublimation and desublimation. Triple point state, right? Triple point state means the state at which the three phases of the same material can coexist under equilibrium state is called triple point state. The state at which the three phases of the material, three phases of the same material can coexist under equilibrium state is called triple point state, right? It is like this. Let us take water in a container. Let us take water in a container. That is the container. I am taking water in a container. Water in a container. This is the water. Above the water surface, assume atmospheric gas is there. Okay? That atmospheric gas pressure is acting on the surface of the water like this. That may be 1 atmospheric pressure. Okay? Then what I am doing is, I am connecting a vacuum pump here. I am connecting a vacuum pump here. Once I connect a vacuum pump, that vacuum pump can lift the gas present on the surface of the water. Once some quantity of the gas is lifting, the remaining quantity of the gas on the surface of the water can contribute low pressure. That means by the time the vacuum pump is continuously lifting the gas, the pressure which is acting on the surface of the water keep on reducing. Okay? Once the pressure on the surface of the water, reaches to 0.00611 bar, at that particular pressure, right, the saturation temperature is 0.01 degree centigrade. At that particular pressure particularly, a part of the water is becoming ice. That means a part of the water is becoming solid. A part of the water is available as vapor. Remaining water is available in liquid state. Once again, once you maintain the surface pressure of the water is 0.00611 bar, at that particular pressure, a part of the water is becoming ice, that is solid state. A part of the water is becoming vapor, that is gaseous state. Remaining water is available in the liquid state. That means the liquid phase, vapor phase and ice phase, these three phases are maintaining, right, maintaining same pressure, means mechanical equilibrium, same temperature, thermal equilibrium, and no chemical reaction between the three states of the same material. Therefore, that system is under chemical equilibrium. If any system is maintaining thermal equilibrium, mechanical equilibrium and chemical equilibrium, then that system is said to be under thermodynamic equilibrium. From this the conclusion is triple point state is the best example for thermodynamic equilibrium. Got that point? Thermodynamic equilibrium means, right, the system is said to be under thermodynamic equilibrium if it maintains thermal equilibrium, mechanical equilibrium and chemical equilibrium. Okay? Here, though solid state, vapor state and liquid state are existing, the three materials are maintaining, three states of the same material maintaining same pressure, mechanical equilibrium, same temperature, thermal equilibrium and no chemical reaction between the three states of the material, chemical equilibrium. Therefore, at the triple point state, the three materials are maintaining same temperature, same pressures, no chemical reaction. That is the reason the triple point state is the best example for, right, thermodynamic equilibrium state. Okay, this particular pressure you can call as triple point pressure, and this particular temperature you can say triple point temperature. Triple point temperature. So that triple point pressure with PT, pressure versus temperature coordinate system, pressure versus pressure which is in bar, and temperature which is in degree centigrade, right. For the triple point state, what is the pressure? Pressure is 0.00611 bar. This is the 0.00611 bar. Right, corresponding to that point, project a horizontal plane representing the constant pressure equal to 0.00611 bar. Corresponding temperature is 0.01 degree centigrade. Try to mark the temperature 0.01. From that point, project a vertical line. Vertical line is representing the constant temperature, that is 0.01 degree centigrade. Wherever those two properties are meeting, that particular state, wherever the pressure and temperature are meeting, that particular state is called triple point state. Triple point state. Triple point state. At the triple point state, solid state is available, liquid state is available and vapor state is available. Okay? Dear friends, remember, below triple point state or particularly below triple point state pressure, right, liquid phase cannot be existing. Below triple point state pressure, the material may be available either in solid state or vapor state. Liquid phase cannot be found. Okay? Now, whatever the phase change process which is occurring below triple point state is called either sublimation or desublimation. Okay? Sublimation means the direct phase change from solid to vapor is called sublimation. The best example is, camphor. At the end of the puja, we are giving haratina, right? Once you give the heat energy for camphor, the solid state of the camphor directly becoming vapor. The solid is directly becoming vapor. Therefore, camphor burning is the best example for sublimation. Similarly, you take the dry ice. Once you keep the dry ice in the free atmosphere, the solid state of the dry air is directly becoming vapor without having the intermediate state called liquid. That kind of direct phase change from solid to vapor is called sublimation. That sublimation process is like this. For that, let us take the ice. Let us take the ice. Here is the ice block. Assume the ice is exposed to a pressure 0.005 bar. That 0.005 bar is the pressure well below the triple point state pressure, because the sublimation is happening below triple point state pressure. I have taken the ice to expose the ice surface to a pressure below the triple point pressure. Assume the ice is initially available at -20 degrees centigrade. At -20 degrees centigrade. Dear friends, remember, if I start to heat the ice at this pressure and at this temperature, immediately ice may not be becoming vapor. That is called sublimation, because corresponding to this pressure, saturation temperature, let it be -5 degrees centigrade. No? At each and every pressure there is a saturation temperature. Like how the water starts boiling at 100 degrees centigrade, when the water is heated at atmospheric pressure. But when you maintain the surface pressure above atmospheric pressure, boiling point is going to increase. Similarly, when you decrease the surface pressure of water, boiling point decreases. The boiling point of the water is not remaining same at the top of the Himalayas and at the ground level. Definitely at the top of the Himalayas, the boiling point of the water is less, because at the top of the Himalayas, the pressure is well below the ground level pressure. The pressure, the corresponding to ground level or corresponding to ground level pressure, water starts boiling at 100 degrees centigrade. At the top of the Himalayas, water may start boiling around 85 degrees centigrade or 90 degrees centigrade, that depends on the pressure. Anyhow, corresponding to, from that what is the conclusion is, at each and every pressure there is a saturation temperature, whether it is for freezing or melting or evaporation or condensation, similarly for sublimation and desublimation. Okay. So corresponding to 0.005 bar, I am assuming this is the saturation temperature, but ice is available at minus 20 degrees centigrade. Then if I start to heat the ice, immediately ice is not going for sublimation. What is happening is, the temperature of the ice is increasing from minus 20 degrees centigrade to minus 5 degrees centigrade. Once the temperature of the ice is increasing from minus 20 degrees centigrade to minus 5 degrees centigrade, that minus 5 degrees centigrade is the saturation temperature corresponding to this pressure. At that temperature and pressure, the ice is directly becoming vapor without having the intermediate state called liquid. That particular direct phase change process from solid to vapor is called sublimation. Got that point? It means corresponding to 0.005 bar, there is a saturation temperature. That saturation temperature is around minus 5 degrees centigrade, approximately minus 5 degrees centigrade. So this is the sublimation state. Similarly, corresponding to 0.004 bar, right, there is a saturation temperature. That saturation temperature may be minus 10 degrees centigrade. So this is the saturation state. Similarly, corresponding to 0.003 bar, the saturation temperature may be minus 12 degrees centigrade. So these are all the saturation states. These are all the saturation states for direct phase change from solid to vapor, called sublimation. You try to join all the saturation states for getting a smooth curve called sublimation curve. Okay, that sublimation curve you can mark like this: the pressure versus temperature coordinate system. This is how the sublimation curve is appearing. The sublimation curve is maintaining positive slope. Sublimation curve maintaining positive slope means as the pressure increases, sublimation temperature also increases. The apex point of the sublimation curve is triple point state. Okay, and the region left to the sublimation curve is solid, right to the sublimation curve is vapor. The direct phase change from solid to vapor, is called sublimation. Whereas the reverse process, the opposite process, you can call as desublimation, is also called sublimation. I am writing ulta, desublimation. The direct phase change from solid to vapor is called sublimation, whereas the opposite process to sublimation is called desublimation. Desublimation means phase change from vapor to solid. That's why I have written ulta. Okay. Similarly, water is available at this particular triple point state. That water starts evaporation at 0.01 degree centigrade corresponding to that pressure. But as you know, when you increase the surface pressure, definitely boiling point increases. Corresponding to this point to 6 bar, this may be the boiling temperature, maybe 20 degrees centigrade roughly. That is the saturation state for evaporation. Corresponding to some higher pressure, boiling point increases. This is the saturation state corresponding to this 6 bar. Like that, when you keep on increasing the surface pressure, the saturation state or boiling point keep on increasing. These are all the saturation states for evaporation. You try to join all these saturation states for evaporation for getting a smooth curve called vaporization curve is also called evaporation curve. That evaporation curve is looking like this. This is how the evaporation curve is looking. The region left to the evaporation curve is what liquid and right to the evaporation curve is vapor. That means the phase change from liquid to vapor is called vaporization. Okay? The phase change from liquid to vapor is called vaporization or evaporation. Generally it is called vaporization, evaporation. And the phase change from vapor to liquid, is called condensation. The reverse process of vaporization is the condensation. I am writing ulta. Condensation, condensation, S-A-T-I-O-N. That is how the evaporation and condensation can be marked. Dear friends, remember the vaporization curve and sublimation curve both are maintaining positive slope. Vaporization curve and sublimation curve both are maintaining positive slope means as the pressure increases, saturation temperature increases for both sublimation and vaporization. And the vaporization curve and sublimation curve both are meeting only at a triple point state. Okay? Similarly, at the triple point state ice is available. That ice is melting at 0.01 degree centigrade corresponding to that pressure. But when you increase the surface pressure of the ice, instead of increasing the melting temperature is going to decrease. Corresponding to 0.6 bar, this may be the melting temperature. Corresponding to 6 bar, this may be the melting temperature. Like that, when you keep on increasing the surface pressure, melting temperature decreases. These are all the saturation states for melting. You try to join all the saturation states for melting, you will get a smooth curve called melting curve. The melting curve is looking like this. This is how the melting curve is appearing, right? The region left to the melting curve is solid, and right to the melting curve is liquid. Okay, right? The phase change from, look at the melting curve. Melting curve is maintaining negative slope. Melting curve maintaining negative slope means as the pressure increases, melting temperature of the ice decreases. Dear friends, remember, for most of the material during the melting process, the volume occupied material increases. But peculiar property of the ice is that during the melting process, instead of increasing the volume is going to decrease. Similarly for rubber also. That means for those materials which are decreasing their volume during the melting process, the melting curve is maintaining negative slope. But for the other materials which are increasing their volume during the melting process, right, the melting curve is maintaining positive slope. Anyhow, this is the melting curve I marked for ice. So this is the solid, liquid. The phase change from solid to liquid, is called melting. And the reverse process, is called freezing. The phase change from liquid to solid is called freezing. Right? Understood? Anyhow, once again, this is the melting curve for the material which are decreasing their volume during the melting process. But for those materials which are increasing their volume during the melting process, the melting curve is also maintaining positive slope. Anyhow, for the liquid water, sublimation curve, vaporization curve are maintaining positive slope. Melting curve is maintaining negative slope. But the three curves are meeting at the triple point state. Okay? For other materials which are increasing their volume during the melting process, the melting curve is maintaining positive slope. It means as the pressure increases, melting temperature. Whether volume is decreasing during the melting or volume is increasing during the melting, the evaporation curve, sublimation curve, melting curve are meeting only at a triple point state. I hope all of you clearly understood. Okay. Dear friends, excuse me, I thought to complete all these concepts, but because of the, right, so because of the elaborate, because of the complete discussion of the each and every concept, right, so I am unable to discuss the remaining important concepts. You try to go through any standard material like pK, Clausius Clapeyron equation, that is also important concept. Other one is chemical dehumidification, go through the pK, right. Another one is what nozzles and diffusers. So three important concepts, right, I am missing to discuss because of the time restriction or time limitation. So with this, my dear friends, I am concluding today's session, right. Thank you, right. All the best and God bless you for those students who are going to appear for the GATE or ESE 2024. Okay, God bless you. Thank you.